On the damn microphone. That's why you couldn't hear me. All right, now you can hear me. Hey, can we settle down? So, hopefully everybody had a chance to watch the videos. I have a small apology to make. The last time I used YouTube, they did not have compulsory advertisements. Shows you how long ago it was that I used YouTube. So putting the pre-videos on YouTube, I'm subjecting you to advertisements, and I apologize. If it's really annoying, please let me know. I would be willing to move it to some other video hosting site. Before I do something random like that, I would like to hear from you, okay? So, but I do want to put it public-facing rather than stuck in Canvas just for only people in this class. So if you have feelings, well, you can email me, you can use CampusWire, you can use the anonymous feedback form, right? Just a quick note, because I think last time I didn't actually go through the syllabus in any way, shape, or form. But yeah, like the syllabus, it's here on Canvas. And things like the anonymous course feedback form are right here for you to click. This is a live updating document. So just pay attention to the versions and the fact that in the first 2 weeks, we're going to keep changing it little bits, right? But it's going to settle down, and I'll remove this big red banner when we've got our full version. Actually, I do know mostly who's going to teach which section at this point, but just a reminder, sections are not this week. Sections start next week. Does anybody have any sorts of logistic questions now that you've had a chance to be here for one full class period? Yeah? Yeah, so the videos are going to be on podcasts, and they should show up, I would think, in Media Gallery automatically. They usually do. Looks like we've got some really fine Wi-Fi in here. Looks like there's something awesome happening. Okay. Yeah, I mean, podcasts should have the recordings from this session here, okay? So yeah, this one's here. The YouTube channel should have the pre-things, and I was uploading, I believe I successfully uploaded it. What? That's not what that link should be. Did I click the wrong link? There we go. YouTube channel should have both the lecture time, because I moved it over there physically, and the pre-videos, right, that you're supposed to watch before coming in class. Okay. So, any other logistics questions? Yes, homework's individual.
So, and the project is just the final part?
Yeah, so the project is the group stuff is only project stuff. Yep.
And there's only one project, that's fine.
So there's just one project, but we will ask you to make a proposal, and we'll give you feedback. And then we'll ask you for a checkpoint to make sure that you've gotten some base level of accomplishment, and we'll give you feedback on that. And then the final turn-in. Good? So my ideal is 4. So then let's do some thinking about how we measure similarity. Because machine learning, like the basic idea is often one of generalization, right? We've seen some data points These data points, they're birds. These other data points, they're not birds. So when we get some brand new data in, if we're going to try to predict, is it a bird or is it not a bird, then we're going to fundamentally be asking questions about similarity, right? We're going to want to ask, hey, is this new data point more similar to the bird data or to the not bird data? Substitute your favorite topic here, right? It doesn't have to be birds, it's just what my dumb slides are. So that's what we want to do. We want to measure similarity. So that's what we're going to talk about today. My logistics slide that I forgot that I had. The first thing that you want to do is to do the syllabus quiz, and it's not on Canvas. That's my bad. No. Shoot, I haven't even put it out yet. Okay, so I don't know where it's going to go, but I'm going to try to put it on Gradescope. Actually, can somebody go on Gradescope right now and see if, not the syllabus quiz, but today's lecture exit quiz should already be visible to you? Yes. That's the first time I've managed to do that. Okay, so the quiz that you're looking at right now on Gradescope, that's something you should fill out after having listened to lecture today, and you need to fill that out within 24 hours of the end of class, okay? Then your access is going to disappear. So remember, that's our kind of participation grade, 1% per lecture period for those quizzes. All right. Data Hub is up for this class. Data Hub sucks rocks, in my opinion. So I'm trying to leave Data Hub behind, which is why we're using Gradescope, not the NB grader you may be used to. Okay? So I highly recommend that you find a way other than Data Hub to do your work. Data Hub is there, you should use it, but Data Hub is unreliable, especially at the end of quarter when everybody's trying to get their projects done. Your own computers may be good enough computation for you, right? Most projects can probably be done on decent laptops. I highly recommend installing Anaconda so that you have your own local copies of Python and machine learning libraries that we will probably be using. You can also use Google Colab. So Google Colab is a cloud service rather like Data Hub. It's slightly different looking than Jupyter Notebooks, but it reads those same files. So you can take any IPyNB and load it up on Colab, right? It just looks different. Okay. For those of you who need some Python renewal, there's a list of resources here for you. I'm not going to go through it. This is for those of you who need it. Okay? So if you're going to do Google Colab, there's resources here for you. You can just click on these links. They're pretty good tutorials. If you're going to do Anaconda on your machine, there's some links there for you. I recommend you do both, to be brutally honest, okay? If you're going to do much machine learning, learning how to use Anaconda or Docker is mandatory, in my opinion. If you're going to do this for a job, you will be using virtual environments like Anaconda, or you will be using Docker, which is a lightweight virtual machine system, right? So let me just take 2 minutes to expose those of you who don't know what these things are. Virtual environments. Who here has ever had a software program that worked, and then one of the libraries got updated, and then it didn't work? Yeah, you know what I'm talking about. That's why we have virtual environments. Virtual environments are ways we can say, this is my software for this thing, and to have it work, it is always going to operate with version 1.6 of Pandas library. And I will never update the Pandas library for this piece of software because it has its own virtual environment that has its own versions of libraries. And I have a different software project over here, and it uses version 2.0 of Pandas. And the fact that this one uses version 2.0 doesn't clash with this one that uses 1.6 because they're separate environments, okay? That's what Anaconda is. Anaconda is a way to make virtual environments and manage virtual environments. So when you're working on one project, you're using its environment and its libraries. Okay? You never get that problem where software stops working because of an update. Okay. Lightweight virtual machines like Docker are one step further because your Anaconda environment can still get jacked when your operating system updates. Okay? Because you can't control the operating system and what it does. A virtual machine loads up an entire operating system, and it freezes your software with Ubuntu Linux version blah, 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 and these Python libraries, and that all runs together. So every time I run this program, I open up a virtual machine with a virtual operating system, its own OS, and its own libraries. So that's completely future-proof, right? In the year 2060, when we're running Docker on quantum computers, we can still run Ubuntu 13, even though it'll be like 40 years old at that point, okay? So Docker is a very heavyweight industrial solution, but if you're going to do work in industry, probably worth your while to learn. Conda is easier to learn, less of a learning curve, but it's less suitable for major industrial application. Okay? Any questions? Learn to use both is my vague advice. Okay, let's do models. So machine learning and in general analysis comes in two forms. Do we really care more about predictions being accurate? Or do we care more about the model that we are building? Let me tell you a little bit about this, right? Oftentimes when we are caring more about making accurate predictions, whether that's predicting the stock market or we had the birdsong thing, classifying birdsong, right? Whatever it is we're doing, being right is what we care about. Okay, simple. But if we're doing science-y kinds of things, often what we care about is not so much whether our predictions are maximally accurate, but whether the model we're making is an accurate reflection of the underlying thing we're trying to study. So typically these frameworks, machine learning often, like if you're using machine learning software or somebody tells you they're using ML, they're probably caring more about being accurate. Okay? If somebody tells you that I'm making a model, they're probably using a framework they're going to call statistics, even though the math is the same, right? So when somebody says they're a statistician, they're usually caring more about the model. When somebody says they're a machine learning engineer, they're usually caring more about the accuracy. But to be brutally honest, the tools are the same. It's how you use them. So let's talk about the tools. We need to get everybody up to speed on some basic math we're going to see over and over. We're generally going to talk about data as being x's, right? So we have some data set. We have an input to our machine learning system. We're going to notate it as an x. If x is a plain old lowercase x, that means it's just one number. It's a scalar. It's a, oh, cool. What's going on here? Oh, it's because I didn't, because I did it playing in a window instead of playing full screen. Doesn't do the automatic stuff. Okay. Right. Scalar value, single value, like, I don't know, somebody's height, right? So we're just measuring one number. It's a scalar. Okay? But we oftentimes are going to be doing not single numbers, but vectors, okay? Not just one number, height, but maybe the patient's height and weight and age as three numbers that go together into a vector to make up the data about this patient. Okay? Remember that our notation we talked about yesterday, boldface is going to be vectors. The vectors have m, in this case, features, or m variables. And this means just each one of those variables is a real number, right? This is in the vector space R sub m, means m long vector of real numbers. Okay. So, but we don't, that's just one data point, that's one patient. We're doing supervised learning, which means we have a data set of many patients. And that data set we can note in two ways. We can do it like this. This is set notation. So this set S is n patients, each of which has a measurement vector of their heights, weights, ages, blood pressure. I don't know what else we have on them, right? So it's a set of data points. The set is n long, so we have n patients in that data set. Make sense? Okay. We can write it as a matrix alternatively. We're going to get to that later. So our outputs will generally be noted y. So that y could be a number like +1 or -1 to denote a binary decision. It's a bird. It's not a bird. Okay? This patient is diabetic. This patient is healthy. Binary decisions. Y could also be, if we're doing a regression, some continuous number. Okay. So our general thing is given an x, what's our y? That's our framework. So y is going to be a discrete number, either +1, -1 for a binary decision, or y could be a real value if we're doing regression. So the last thing is the model we use. Because we have x's, we need to get y's. How do we do that? We use a model. The model is going to have parameters that we're going to call W. Okay? W usually stands for weights, right? And weights are going to be a real vector that's the same size as the inputs. We may also have a bias term, which is going to be a single number, a scalar. Now, what does this look like? Hey, wait, that looks familiar. That's a linear equation, right? You've maybe in high school, you knew it as mx plus b, right? But it's the same deal. W just means it's multidimensional now. It's not a single x. There's multiple x variables coming in a vector. And it's not a single m slope, mx plus b, but the weights are the slopes with respect to each one of those x's. Okay? So to break this guy down, it's actually something like this. It's w0 times x of 0 plus w1 x of 1 plus ... right? wm x of m plus b, a constant. When it's y equals mx plus b, what do we call that b? The bias, but also like, you know, when you have a... Sorry, I didn't hear. Yeah. The y-intercept, exactly. Right? Remember that? So, same deal here. That's what the bias term is. Without that bias term, our lines can only go through the origin point. They can't go anywhere else. Okay, so yeah. This dot, that's a dot product, right? And if you don't remember dot products, you should definitely take a look at the video I recorded before class. Okay, so this notation that I'm showing here, there's stupid mathematicians. There's more than one way to write this. And so sometimes you'll see it in this kind of notation, and sometimes you'll see it like this, and sometimes you'll see it like this. These are all equivalent notations. The only difference between them is roughly style points, right? Means the same thing. Just want you to be aware that you might see the same thing in different notations. Okay, so we've talked, and let me just go back 1 second. Right, these W's, again, these W's are the model. So I want to emphasize to you that predictions are Y's, and W is the model we're using. Okay? All right, my stupid slide builds are super slow. So yeah, here's a little science story for you. Thousands of years, people have looked up at the sky and seen stars, right? And it's pretty cool. If anybody like me grew up in the middle of nowhere, you could see the Milky Way just walking out your back of your house. It's really awesome. Most of humanity lived like that most of the time, but most of us don't today, because you live in San Diego. But when you look at the sky, it's really easy to notice that most stars stay exactly together. While they move across the sky, they maintain the same orientation with each other. But one set of wandering stars, they don't do that. One night it might be here, and the next night it might be here, and the next night it might be here. Those wandering stars, wandering star in Greek is something like planet. I'm not a Greek expert. They're planets, right? They move around compared to the rest of the stars. And when you look at the path of Mars across the night sky, like if you always take your picture of Mars at exactly 11:06 p.m., right, what you see is this. It moves through the night sky. It seems to be moving in one direction. You're like, that's cool, I get it. And then suddenly it jinks on you. And then it moves forward again. And, you know, if you're an ancient person, you got no idea what the solar system is. You're like, what the hell's going on here? How can we predict what this wandering star is doing? Because it just kind of randomly seems to go backwards on itself, and I don't understand when or why or how. Okay, so ancient people looking up at the sky, trying to figure out science, you know. So for probably 1,000 years, the default idea of what was going on is what's called the Ptolemaic model of the solar system. So in the Ptolemaic model of the world, or the universe, I shouldn't say the world, the universe, the Earth is the center of everything because that's what God intended, people, right? Human beings, we're on Earth. Earth is really important. It's the center of the universe. And everything else that moves in the sky is moving around the Earth. So the sun is swinging around the Earth. Mars out here is swinging around the Earth too. But that moving backwards on itself, that's called retrograde motion. The way Ptolemy and similar philosophers said that was working is that not only is Mars swinging around the Earth, it's also swinging around its own orbit. So the backwards motion is when Mars is doing this part of its own orbit. It's like moving backwards with relationship to the Earth. Okay. Kind of crazy, complicated Rube Goldberg kind of stuff, right? So if you're ever in a museum, you can see these armillary spheres. They're really cool. There's one in the what's the name of the Air and Space Museum down in Balboa Park? It's a small one, but there's these giant ones that are like bigger than humans, like this, that are clockwork mechanisms meant to represent the motion of planets through the sky. Okay, doing this kind of weird motion. They're really cool to look at. Okay, along comes this guy, Copernicus, and he says, "You all are crazy. That's not what happens. The Earth is not the center of the universe. The sun is the center, and the Earth moves around the sun. And the Pope said, "Heretic, burn him," right? So even though it was right, the thing is, what's happening is, here's Earth moving through its orbit. Here's Mars moving through its orbit. We're on the inner track. We're moving faster than Mars because we're on the inside track, like, in NASCAR, right? And so when we're looking at Mars one day, we have that kind of view, and then we have that kind of view, and then as we pass Mars, it seems to be moving backwards. Okay? Yeah?
Why was the Pope so misrepresented?
You'd have to take a history class for that. Because God said so is my vague idea. Okay. So here we have two competing models. Now let me be clear. The Ptolemaic model is just as good at predicting the motion of Mars through the night sky. You can come up with where Mars is going to be on any given date using Ptolemaic math. Okay? You're not wrong about your predictions, but you are wrong about the process that's happening. Okay? So this is why I told the really, really long story. Because there is a difference between caring about models and trying to accurately reflect reality and only caring about nailing the predictions. Most machine learning would be perfectly happy with a machine learning system that was Ptolemaic in nature. Because all we care about is predicting where Mars is going to be. All we care about is predicting where the stock market will be in 3 weeks. We don't care if we're accurately representing the processes that lead to the stock market being at a particular value. Okay? So this is what I'm trying to get across to you. There is a fundamental disconnect in method between when you care about models and accurately reflecting the true process underneath, or when you just care about predictions. Our software will reflect that. If you're trying to make a linear regression and you care deeply about the linear regression reflecting reality, you should use a statistical package like stats models, like we may be introduced to you in COGS 108. If you're going to use a machine learning package to make a regression, so we're going to teach you a machine learning software package called scikit-learn. Scikit is a machine learning package. It tends to care more about predictions than model accuracy. Scikit makes assumptions that everything is about making accurate predictions to the training set. And it changes the weights. It will get different answers for a linear regression than stats models because it's chasing by default prediction accuracy, whereas stats models by default is chasing making an accurate model that you told it to make. Okay? So, different frameworks, same ends of things, right? So if we only care about prediction, we really only care about that y. We care that our y is accurate and that our predictions have low error. And if we care about modeling, what we really care about is that w. We care, is that w reflecting reality? Is the form of the equation a good form? And are the w parameters themselves maximally accurate given the data we have? Any questions? Okay. So, supervised learning, right? This is our recap. It's a prediction task. Yeah?
Actually, I was wondering, if you get the model right, shouldn't it always be more accurate than focusing purely on the...
No, because overfitting. If you care about maximal accuracy on your training set, you can be overfit, right? So, and if you care maximally about an accurate model, you may not get the best possible prediction error on the training set. Oops, so yeah. So we've got some data. We've got the right answers for that data. We know what the answer should be for that data. That's a labeled data set, okay? And that labeled data set will be denoted training set, right? This is what we train our model on. And we don't, when we want to know how good is our model, we don't train it on the same data, we don't test it on the same data we trained on, right? Because remember, we discussed back on Monday, machine learning systems are super powerful. Whatever data set you give it to train on, it's going to fit those parameters W, not just to the process, but to the noise too, right? Every data set we're going to work with has got some truth obscured by some measurement noise. And machine learning systems are so powerful, we know they're going to pick up on the noise, almost certainly. So it's going to do better on its training set, on data it is trained on, than it's going to do on data that you collect next Thursday from the same process. So that's why we always have a separate testing set. Data which it never was trained on, but this is what we're going to use to evaluate how good our model is, okay? Because if we ask how good our model is on our training set, we're going to get a very optimistic answer. Does that make sense? Okay. So, just a reminder, I did some linear algebra review before class. 3 blue, 1 brown's probably way better. Khan Academy might be another good choice. Okay. Why do we use linear algebra? Because everything in machine learning is represented as a vector. So a data point, like if we're tracking, I don't know, something that moves through space, like a fighter jet. Maybe we've got like a machine learning system trying to predict where a fighter jet is in a video game in a shoot 'em up, right? So we have inputs, the X, Y, and Z position of the virtual fighter jet in the video game, and its velocity in X, Y, and Z coordinates, right? Data points are going to be represented as vectors. So if we're trying to predict whether or not a house is going to sell, maybe we get a vector like this as our data, as our inputs, as our X, right? So fundamentally, a vector represents a data point. How does that work? Well, if we have some representation of animals like this, where we've got the animal's mass and how loud it is when it makes a call, well, maybe we plot just those first two of the, I don't care how many variables there are, so we just want to show just the first two so we have something we can look at. And we plot our animals. And the tiger vector, well, it's, this mass variable, that's x1, and it's that decibels variable, x2, right? That's where a tiger is. And so when we're doing some sort of machine learning system that's trying to separate birds from not birds, what happens is we put a decision boundary in there, right? And that decision boundary can also be represented as a vector. So how does a decision boundary vector work? So with any kind of line, you may be used to the idea that we would use the coordinate system to represent the line itself. So that's not the convention in classification machine learning. In classification, what we do is we represent a normal vector to the decision boundary. Okay? So that red line is the line between birds on this side and not birds on that side. Okay? So for this boundary, we represent it with the normal vector, this guy. So by determining the perpendicular vector to the surface, we uniquely determine the surface. Why do we do it this way? Because we need to have sides to that decision boundary. we need to know what side this is and what side that is. So if we just used like the line itself, like as the vector, that doesn't tell you sides, okay? But having a normal vector tells you sides. You're either on the side with the normal vector, or you're on the side that doesn't have the normal vector. Okay? That's why the convention for machine learning is the perpendicular normal vector to the decision boundary. All right, let's do some math. So, and just to be clear, the idea of a decision boundary itself, well, if we take the dot product of this weight vector and any data point, right? So this is my x, this is my weights. The dot product of weights and x is 0 at the decision boundary. Yeah?
So this is only for classification, right? So, because of that, the size of the vector would not matter?
Oh, yes, you're correct. The size, the magnitude of it doesn't matter, only its direction. Absolutely correct. We're going to talk about that in the next slide. Yeah?
Why are we doing this relative to normal vectors instead of like inequalities?
Instead of what? Was
Inequality?
an inequality. Right, they're equivalent. So here's how the inequality works, right? Guess what is bird side or positive side? Sorry, let me use some consistency of color here. So this is positive class side, where things are, quote, +1. And this is negative class side, where the label is -1, okay? So something is positive class when there's your inequality. And y is equal to +1. Sorry, my handwriting gets atrocious sometimes. Y is equal to +1 if and only if w dot x is greater than 0. Is that the kind of threshold inequality you were thinking about? Okay. Because the decision boundary is where the dot product is 0. Why is that where the dot product is 0? Who watched the video? What is a dot product is the kind of answer to that. What is a dot product? Hold on, you've been in. I want to encourage somebody else. Everybody can play. It's okay if you're wrong. Yeah?
It's a multiplication of the component of one vector for another vector.
Yeah, so if we have two vectors, right? There's one special word I'm looking for. So these are perpendicular vectors, but more generally, what is the dot product of two vectors? The what? So it's normal when they're perpendicular. Well, okay, so everybody's on orthogonal perpendicular, but if we have non-perpendicular vectors and we take their dot product, or any two vectors and we take their dot product, what does the dot product give us? Louder, please. Yeah, so the component or the projection of one on the other, okay? Think of it like this. Okay, that's my projector, right? The viewpoint of that projector, this is the projection of this vector onto that surface, okay? This is a perpendicular projection. It disappears, right? Because it's orthogonal. Sorry about my hand, but right? It's orthogonal. The projection of this vector onto this vector is 0. Now it's maximum, the biggest projection it can get. the angle between these two vectors we can see in the projection, literally in the projection from the viewpoint of the projector, okay? That's the dot product. The dot product disappears to 0 when things are orthogonal, perpendicular, all those words. But in general, what the dot product gives you is it gives you the projection of one vector onto another. How much of this vector x is on this axis here. Does that make sense? If it doesn't make sense, go watch 3 blue, 1 brown. I've done what I can do. Okay. Now, going back to this picture that we had a second ago, maybe it makes a bit more sense, right? The projection is 0 right now, right? Because these are orthogonal. Right? Here's the vector to the x. So they're orthogonal, so the projection is 0. That's why the decision boundary is 0. That's why when the projection, so what if we have another data point over here, where the eye is in birds, okay? So this is that vector, and the projection onto the w is going to be a positive number. We're on the positive side. We're on the bird side. If I have a different data point over here, okay, its vector looks like that, and its projection is going to be negative. It's going to be this projection right there, right? So this is going to be a negative number, this dot product, for the green data point. We kind of getting it? All right. So that's why we denote classification boundaries with the normal weight vector. And the dot product of wx, well, that tells you whether you're in bird territory or not bird territory. Okay. So we did a lot of stuff all in one go. And I totally ignored my slides and just drew over them, so that's fine. Now, we had the intuition earlier that distance of the vector doesn't matter, only its direction. So let's talk about that. So first off, because it's going to be a homework exercise, right? Hint. How can we even find the w vector if you know where the line is? Okay, so if I gave you this coordinates, this slope for that line, right? How would that look? Well, let me draw in this. Let's say there's that vector v that we were given there, right? That vector v is going to be, so the x component is 1, right? 1. The y component is 1.2. We know that vector v because we know the slope of the line, and again, you're going to be asked in a homework thing to do this, okay? How do we get the w? It's perpendicular, yo. So how can we get the w? How could I write down w? Yeah? Okay, so you can definitely do that, but I'm going to say you can just look at this and write it down without even doing that, because it's just reflected about this y-axis, right? Like this angle and this angle are the same. And this distance and this distance are the same. So you can just write it down. Does anybody know how to just write it down? Yeah?
I think you find the reciprocals of distance.
Sorry?
The reciprocals?
Yeah, so basically this, right? So if you look at this, you know it's pointing in the negative x direction, right? It's the same y, negative x direction, so it's just this. Right? Okay. So Okay, but again, we only care about direction. We don't care about magnitude. So for convenience, we often specify what's called a unit vector weight. A unit vector weight means it's just one long, but in the same direction as our W vector is. Okay, so it's just one long. How do we get to one long? Well, Pythagorean theorem, so the magnitude of W is square root of W1 squared plus W2 squared, right? Sorry about my bad handwriting, but that means that this is 1 squared plus 1.44, right? 1.2 times 1.2 is 1.44. So that's just 2.44. I should bring my square roots everywhere. Okay? So that's the magnitude, the square root of 2.44 of that vector. Just Pythagorean theorem, right? Okay, so to get, sorry, I put my crazy stuff right on top of that. So the magnitude of a normalized vector is just going to be these original weight values divided by this, right? So it's minus 1 divided by the square root of 2.44, and it's 1.2 divided by the square root of 2.44. Does this make sense? If not, you can watch it back on podcasts. Okay. So, oh God, I keep meaning to remove these slide transitions, right? The dot product. The dot product gives you a scalar value. Takes two vectors, makes a single scalar number out of them. That scalar number represents how much projection vector 1 gets onto vector 2, right? You can note that in different ways. They're all equivalent notations. Okay. So the dot product is largest when vectors are parallel to each other. And it is smallest when they are orthogonal to each other. Okay, I'm getting really upset at my slides transitions. So when they're biggest with each other, it's the magnitude of vector A multiplied by the magnitude of vector B. That's the biggest it can be. So when vectors are very, very big, their dot products can be very big. And when vectors are very small, then their dot products are very small. Okay. Dot product is fundamentally a measure of similarity. If we take a feature vector, in this case something which is one-hot encoded, if you don't know what one-hot encoded is, you need to watch that video. Okay, we had two animals, sparrow and chipmunk. They have different vector representations in terms of their weight, whether they fly, whether they lay eggs. So if we dot product sparrow and chipmunk, we get a number. If we dot product sparrow and bat, we get a bigger number. Why? Because sparrow and bat are more similar to each other because they both fly. Okay? Sparrow and chipmunk, they're just complete opposites. Okay, so chipmunk and bat are also fairly similar to each other because they have much more similar in that they don't lay eggs and stuff like that. Okay, this dot product is a measure of similarity. Remember, we started this whole thing with the idea that we want to measure similarity between different vectors or different data points, or between a data point and a model. Okay? So we're almost there. I didn't quite finish everything I wanted to finish today. I know that there is a question on the quiz, the exit quiz, which I did not cover. But if you watch the video, the pre-video, you should be able to do that question correctly. Okay? Have fun. See you on Friday.
I think I might be wrong. Can I just go back a slide?
Yeah.
I think you did the vector thing wrong.
Oh, did I?
Is it? Oh.
Yeah, that's stupid slide
This one,
transitions.
shouldn't it be flip? Isn't it negative 1.21? Am I wrong?
So this is the X,
Yeah.
right? So this
Shouldn't
is
that become the Y because you like flip at 90?
no. So we're still measuring it in the same coordinate system,
Okay. Yeah,
right? So it's negative. So this is -1 now because it's just a reflected vector.
Okay. Oh,
Right?
you were just reflecting it. I see. Cool. Okay. And second thing, since I'm not on the grade scope yet, is there a
Yeah.
way to make up those
Oh, shit. I don't. Okay, let me see if I add you as an observer
Okay.
to Canvas. That was going to take an hour or two to take effect.
Sure.
Maybe that gives you access to Gradescope
Okay,
automatically. I don't know if it does.
Hopefully.
If it doesn't, email me and I will be able to later this afternoon manually add you to Gradescope.
Okay, fantastic. Thank you so much for helping with
Yeah.
this.
Hey.
For the office hours thingy.